In this video, we will simulate a casino-like betting game. It's a very simplified version. I thought of simulating the roulette game because of the so many rules. The code and the video will becomes too long, so I choose a very simple game. Okay, it's a spinning game, so it looks like this. It has these three divisions: yellow, red, and blue, and you bet on one of the colors. Okay, so let's say you bet on yellow, and if the arrow lands on yellow, you gain $1 or 1 point. And similarly, if you bet on blue, and if it lands on blue, you will gain 2 points. And red is where you lose points or money. If it lands on red, you will lose 3 points. So if you bet on yellow or blue, but if it lands on red, you will lose 3 points. Okay. Now, let's say each game consists of 10 rounds. So, which means if you are playing one game, that means you are actually playing 10 rounds. Okay. So we will simulate this game for a 1 million times, and we will ask a number of probability related questions. Now, by now you are already familiar with Monte Carlo simulations, etc. Here, uh, the important thing is, how do we frame this problem? I mean, how do we translate this game into this random numbers sampling thing, right? For example, here we are saying if it lands on the yellow region, you will gain 1 point, right? So the yellow region consists of 50% of this circle, right? So the arrow lands on one of these regions. These three regions consists of 100%, and yellow consists of 50%. So what do we do is we simulate a random number between, let's say, 0 to 1 or 0 to 100. It doesn't matter, between a fixed width. And then let's assume for simplicity it's between 0 to 1. If the random number happen to be between 0 to 0.5, then we say the arrow has landed on yellow region. Or you can say it is between 0.5 to 1.0. So it is up to us. So as long as we take that 50% of the random number range, that would be the yellow region, right? So for example, here what we are doing is we are defining a function. We are going to, for each game, and each game consists of 10 rounds, right? So that's why we are looping over 10 values. Now we generated a random number. Now we know this value is going to be between 0 to 1. So here what we are doing is, if the value is below 0.5, we are calling that yellow region, and our number of points will increase by 1. So let's say we begin with 0 points, but let's say we are allowed to play this game as long as we want, even if we are with negative balance. Okay. Or you can frame this as, if R value is greater than 0.5, then also you can call it a yellow region. Okay. And then let's look at the blue region. So this consists of 25% of the circle area, right? Then we can say if the random number is greater than 0.5 and less than 0.75, that we can call blue region. Or we can say if the random number is greater than 0.75, which means 0.75 to 1.0, which is about 20, which is exactly 25%, right? So we can either frame this as R greater than 0.5 and less than 0.75, or R greater than, or the random number greater than 0.75. So that would be blue region. So our points will increase by 2 points, right? And finally, the remaining region, which in this case would be greater than 0.75. That's what remaining, right? So up to 0.5, it's gone. Between 0.25 to 0.75, that's also gone. So the remaining region, if R is greater than greater than or equal to 0.75, that would be this red region, and we lose 3 points. Okay. So the tricky part, as I was saying, is, I mean, this is still a very simplified problem. In the upcoming videos, we will see bit more trickier and realistic problems, but translating this into these random numbers samplings is the real tricky thing. Okay, and then after playing one game, uh, which consists of 10 rounds, it will return the number of points. Okay, so let's define these points as a list. We are going to play this game 1 million times, and each time 10 rounds. And after the 10 rounds, we are counting how many points we have. So we have started with 0, and here, so we call the function, meaning we are playing the game, and then this function returns the number of points after the game or the 10 rounds, and we have collected the points into a list, right? So this is how it looks like. Now the length of the points is going to be 1 million because we have played the game 1 million times. Now if you look at the first 10 elements, this is how they are, which means in the first game, after 10 rounds, we have gained 4 points. In the second game, again after 10 rounds, we have gained 10 points. Whereas in the third game, we actually lost, right? So we begin with 0, but by the end of the game, after those 10 rounds, we have lost 10 points or $10, right? Now we'll ask a number of probability related questions. Okay, and we can answer all those questions just by using this points list, right? Which is of length 1 million. So let's start with a simple question. What is the probability that we will make a profit by playing this game, right? And the game is consists of 10 rounds. Okay, so all we need to do is we go over all the values in this points list, and we'll check how many of them are greater than 0, right? We are looking for profit, so the points or the p-value should be greater than 0. Now this logic will return a boolean, true or false. Now when we compute the sum, all truths are considered as 1, so this will return the number of times the values in this list are greater than 0. Okay, that means we are making a profit in those games. So the probability is the number of times we made the profit and the total number of games we have played. Okay, so this just rounding the probability to 3 decimal points. Now then finally, if we are printing the probability of making a profit by playing this game. Okay, so it's 0.63. All right, and then let's reverse this question. What is the probability of making a loss, right? So all we need to do is check or the count the number of values which are less than 0. So which are less than 0. So only this thing is changing. So the probability of making a loss is close to 0.28, right? 0.29, let's say. Now it could be that we profit or loss. So let's look at that probability as well. So the sum of these 3 probabilities should be equal to 1 because there are only 3 possibilities. So it's 0.63, 0.93. Yeah, that's right. That's right. Okay. So 0.63 plus 0.28 plus 0.07, that would be equal to 1. Now we have some rounding of error because we are rounding the values to just 3 decimal points. So to answer this question, we just need to check how many times we have 0 as the points, right? So we begin with 0 and we are checking how many times the p-value or the points value is equal to 0. So that probability is about close to 0.07. Okay, and then let's ask more questions like, what is the probability of making a profit greater than x? Okay, so again, very simple logic. So let's say here we want to compute the probability of making a profit, let's say greater than 0, greater than 1, greater than 2, so on and so forth, up to let's say 20. So in the final question, here we are asking a number of questions. What is the probability of making a profit of greater than $20 or points? Okay, so we are looping and for each time we are counting how many times the profit is greater than the reference value. Okay, a very similar thing. So here it says the probability of making a profit of making any profit, right? Greater than 0 means it could be 1, it could be 2, it could be 10, anything, is 0.634, which should be equal to this value, right? This is the probability of making a profit. Now, as you can see, with this value increasing, obviously the probability will decreases, right? And this says we cannot make a probable profit of more than 17 points. Okay, so 16 is the maximum. So by playing this game 10 rounds, even if it lands on this, let's say the blue, every time, the probability of making a profit, I mean, I guess if it lands on the blue every time, we will make uh, a profit of 20, right? We will make a profit of 20, but that probability is so small that when we did the rounding, it became 0. Or maybe let's remove this rounding thing. We might need to simulate more times so that that also happens. Yeah, here we can see, right? This is extremely small. So when we played the game 1 million times, we have played the game 1 million times. In those 1 million times, only one time we have made a profit of 19. So the probability of making a profit greater than 19 is just 1 in a million, right? Um, so again, as this number increases, the probability decreases, and it seems like the most likely profit we will make is somewhere around 2 or 3, something like that, right? So in this region, the probability is still greater than 50%. Okay, and similarly, we can ask what is the probability of making a loss greater than some value, right? So all we are doing is we just reverse this, and we are checking how many times the value is less than this reference value, right? So again, it says it's impossible to make a loss of greater than 20 points, right? So even if we uh, uh, right, and the most likely loss we make, it's somewhere around some 2, 3, or 4 points, right? So in this region, these are the high values, right? And finally, we can ask the probability of making some exact profit, right? So here we have asked the probability of making a profit greater than a specific value, right? Whereas here we are asking the probability of making an exact profit of 1 point, 2 point, 3 points, etc., etc. So obviously these values will be smaller, because here when we ask this question, this probability includes all these values as well, right? So that whereas here it's the exact value. So that's how it goes. uh, All right, that's all I want to say. As I mentioned, roulette game should have been much more interesting, but it has too many rules, so the code will become too lengthier in the video also. But you understand how we translate the game uh, into these random numbers, right? By generating and sampling these random numbers, we can simulate any betting game we see in casino. Okay, and we can compute the probability of us winning versus the host winning, etc. Okay, that's all for today. Thank you.